Good morning, class. I believe we can
Morning.
start. Morning.
Good morning.
Okay, thank you. I want to start now because I have a meeting by 10. So I think we will start now. Welcome to yet another class with me. I believe this will be my last class with you. Then another lecturer will take over in the next class. So in the last few lectures, we talked about alcohol. So today we want to talk about phenols. Like I said in the previous class, that phenol is also carrying an OH uh, functional group, but the OH is on benzene ring. Because the benzene ring, when it is a substituent, becomes, okay, sorry, let me record. I want to record. So once again, welcome to CHM 213 class. So today we are starting with phenol, and phenol is just like alcohols that has the hydroxy group attached to it. But the hydroxy group is attached to a benzene ring. And that's because benzene ring as a substituent is called phenyl, the phenyl substituents. So adding OH to it, it becomes phenol. It is actually one of the organic compound that has its own unique name. The name does not follow the normal pattern for the IUPAC system that we know about other compounds. So phenol has its own name uniquely. So a phenyl ring attached to an OH becomes a phenol. So there are class of chemical compounds that have OH, like I mentioned, and this is attached to the aromatic ring, hydrocarbon ring, which is benzene. And so that is phenol. So the molecular formula is actually C6H6OH. And they are widely used in industrial processes and the manufacture of so many useful products that we use at home every day, like plastics, like disinfectants that we use, our antiseptics, and some pharmaceuticals and other products. So let's look at this. So this is the structure of phenol. Like I said, it consists of a benzene ring and an OH is attached to it. Phenol is a compound that is slightly acidic because of this OH, because the OH is carrying a positive charge and a proton. So it can lose that proton. So when it loses that proton, it becomes phenoxide ion. When you lose the proton, the 6,6H5 oxygen that is left carries a negative charge, and the hydrogen, the proton is released as a positive charge, and that is what gives it is a acidic parameter, acidic characteristics, and the pK is around 10. So it's actually acidic, although it may not be as acidic as the normal acids we know, but in terms of organic compounds, it is acidic. So that is one of the characteristics I want you to know about phenol, because we are going to use that in most of its reactions. Then there are some types of phenol that we need to know. The one I showed you just now is this is a monohydroxy phenol because it is carrying only one hydroxy group. But when it carries more than one hydroxy group, then it can be a polyhydroxy group because it can then carry two hydroxy group or three hydroxy group, like we have in resocinol and pyrogalol, which we see later just now. And then we also have what we call substituted phenols. These have other functional groups that are attached to the phenol aside from the hydroxy group. And the groups may be methyl group, it may be carboxyl group, it may be the halogen group, or any other group that's attached to it, or a sulfonide group. So these are the examples of phenol that we have. The first one is phenol, that is the monohydric. Then this, you can see that this is a phenol carrying another substituent. So this the second one, which is p-cresol. P is standing for para-cresol. It is actually a substituted phenol. So the cresol can come in three ways because we have the ortho, the para, and the meta position. When you have like if you look at this phenol in the first compound, there are positions around the benzene ring, aside from the one carrying the OH. So the two that are next to the carbon carrying the OH are actually called the para positions, and then, the ortho positions, and then the next one are called the meta position. Then the last one that is opposite the OH is always called the para position. So that means when incoming substituents are coming on this phenol, it can either go to the two ortho position, to the two meta position, or to the para position. So that's why we have paracresol, orthocresol, and metacresol. And these are also substituted phenol. You can see that the substituent is actually a benzyl ring. This is a benzyl. A benzene ring with a CH2 is called a benzyl ring. So this is 4-benzyl 2-chlorophenol. And the other one, the phenol is carrying two species, two different substituents, a nitro and an ethyl group. So you just it's now called 4-ethyl 3-nitrophenol. So when you are doing the numbering, just the number of the H becomes number one. That okay, let me just go to the nomenclature of phenols. This is the phenol. I've already told you that it is the parent compound that carries the OH. So whatever is there, it's either you mention the position, or if it is just one substituent that is on it, it is better to use the ortho, meta, and para. But if there are more than one substituent attached to the phenol ring, like we have in this third compound, then you have to mention the position of the substituents you are talking about. But for a mono-substituted, this is a mono-substituted phenol now, because phenol is already there. So you can mention whether it is also, whether it is meta, or whether it's para. Like this is M-cresol, meta-cresol. But here we have two substituents aside from the OH. So you just have to mention it. And you number it like we number normal organic compound in IUPAC naming, that you make sure that the substituents carry the smallest smallest number possible. So this is 2, 5. Because if you do it the other way, it will be this, we can now carry 3, 6. So 2, 5 is better than 3, 6. So it's better to go clockwise here now than to go anti-clockwise. In some compound, it may be anti-clockwise that will favor the smaller integer. So you have to look at this. So this is 5-fluoro, 2-methyl. Then you wonder, why are we putting 5 before 2? You know that you normally, according to IUPAC that you have been taught severally in your 100 level, you have to look at alphabetic order. So chloro comes before M, C comes before M. That's why it is 5-fluoro, 2-methyl phenol. So these are other examples. This is benzene diol, 2OH, 1,2-benzene diol. This is 1,3-benzene diol. This is 1,4-benzene diol. And this the names under them are actually, this is the resorcinol I mentioned the other time. This is hydroquinone. And this is this will be, as a mistake here, this is hydroquinone, not hydroquinone. It should be all. Then this is procatechol. So these are examples of a di-substituted phenol carrying OH. Then this is naphthol. This is a phenol carrying another benzene ring. Another benzene ring is fused to it. This is 1 naphthol. This is 2 naphthol. This position is 1, followed by 2, 3, 4. Then you shift to 5, 6, 7, 8. The fused carbons are now 9 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is 1 naphthol and this is 2 naphthol. They actually derive from naphthalene. Naphthalene is 2 benzene ring that is fused together without OH. So naphthalene, this naphthol is the derivative of naphthalene. And this is p-hydroxybenzoic acid. So now you see that the name is not phenol again. This is because the carboxylic group have higher priority and preference than OH. So that's why the name is now benzoic acid, because this group, the carboxyl group, has more preference. When we rank functional group in order of priority, you already know how we rank them from alkane, alkene, alkyl, alcohol, aldehyde, ketone, carboxylic acid. So carboxylic acid, if it is on a benzene ring, it will be the parent compound and not the OH. So that's why it changes. So here now, the OH is now standing as a substituent. That's why it is p-hydroxybenzoic acid. And you can see too, because ketones are also higher here. So this is also now acetophenone. This compound, sorry, this substituent, this acetyl group is aceto. So this is acetophenone. And then the other substituents, this is acetophenone. And then the other substituents are then named accordingly in their proper positions: 2-hydroxy, 4-methyl acetophenone, showing that we are using the benzene and the acetyl group as the parent compound, because ketone is more important or has more priority than that. Please, there's a problem here which I want you to do on your own. That's a write the structural formula of each of the following. So try and do it on your own at your own time, please. And now, the OH group of phenol allow hydrogen bonding to other phenol groups because of the OH. In fact, phenol has a very, very good hydrogen bonding characteristics. They can bond to each other when they are together. And so that makes it very, automatically that we make their bond very strong, and it will also increase their boiling points or whatever. So and this can be compared to compounds of similar size and molecular weight, because hydrogen bonding in phenol raises its melting point, its boiling point, and also solubility in water. It improves the solubility in water, but increases the melting point and boiling point because of the bonding, the strong bonding of the hydrogen that is there. Please, I don't want anybody to stop this class today at all. Please, everybody should mute. Okay, so this is the hydrogen in water. It also apart from forming hydrogen bonding with each other, they can also form hydrogen bonding with water. This is a water molecule in the middle here, and it can bond with, this is a phenol, and this is another phenol here. So they can bond together to form hydrogen bonding. So then there's also what we call intramolecular hydrogen bonding. That is, if the phenol is carrying NO2 on the ring like we have here, this is NO2 and there is phenol. So the H of the phenol, phenol can interact with one of the oxygen of the NO2 to form intra. The one we have up here is called inter. That is between two different molecules. The one up here is called intermolecular hydrogen bonding. Then the one in between, because the two species or substituents that are interacting forming the hydrogen body are in the same molecule. So it is called intramolecular hydrogen bonding. Then acidity of phenol, like I said, I've mentioned it already, that they are acidic because they can lose their proton. But even then, they are less acidic than carboxylic acid and other acid, because carboxylic acid has a pKa of 5, phenol has a pKa of 10. So the lower the pKa, the more acidic a compound is. So they are acidic, but they are still less acidic than carboxylic acid. Now, let's explain and compare the ionization of ethanol and phenols. Ethanol is an alcohol. Phenol is also an alcohol, but because they both carry OH, but because phenol is aromatic, we don't group them under alcohols. It's only the aliphatic ones that we group as alcohols. So ethanol is an example of an alcohol. They both have the OH here. So if this bond between the O and the hydrogen is broken, we have a proton form and we have an ethoxide formed. And if the bond between phenol, OH, is broken in phenol, we also have a proton and we have a phenoxide ion. But if you look at the phenoxide ion, the phenoxide ion will be more more stable because of the localization will occur here. It will be more stable than this one. Here, there's no delocalization occurring. There are pi electrons inside the benzene ring, which can move around, especially with this negative charge, because negative charge here is also extra electron. There are also extra electrons. The pi electrons are also extra. So they can move around. This negative charge can move around and stabilize this phenoxide ion. Please, can you please move? Makanjuola, please mute. So, like I was saying, the phenoxide ion is stabilized because of the, okay, let me show you in the next slide. I think I have it in the next slide. So this is the next slide. So this is it. So this is the phenoxide ion. So electron, we have electron delocalization because the negative charge on the oxygen can move around because it has familiar electrons inside the ring that it can interact with, unlike the aliphatic alcohol that doesn't have it. So the negative charge can move from one bond to the carbon to the other. Like we can have it can be here, it can move here. So it can move to the auto, to the para, and back to the auto like we have it. So the negative charge in the phenoxide ion is shared. Ella, please mute. Ella, mute. So the negative charge, Ella, please mute, please. The negative charge in phenoxide ion is shared by the oxygen and the carbons that are in auto and para to it. And so the localization of this negative charge strongly stabilizes the phenoxide ion, just like I mentioned earlier. So that's why it is a stronger acid than even alcohol. So this is so it's a stronger, so phenol is a stronger acid, and then the phenoxide and the hydroxide ion is a stronger base. So this is the phenoxide ion, and so it can form water. So when they react together. So when phenol and water reacts together, and hydroxide reacts together, we have phenoxide ion. The OH abstracts a proton. The base, this is a base, now a strong base. If you add it to a strong base, because it's not acting as a strong acid here. Stronger acid reacting with a base, the base abstracts a proton just like in the normal neutralization reaction. And then you have the phenoxide ion and we have water. So this is another reaction. This is a weaker acid, and this is the weaker base to give a stronger. So it depends on what you are reacting it with. If you react it with an hydroxide ion, the phenol will be a stronger acid. If you react it with something like bicarbonate, because bicarbonate already have an hydrogen here, then the phenol becomes a weaker acid, and then this becomes a weaker base. But in all, the two of them will give the phenoxide ion. The phenoxide ion can be weak or strong, depending on what you are reacting, the base you are reacting with this. The subsequent effects on the acidity of phenols. That is what we call electron withdrawing groups and electron releasing groups. The electron releasing groups push electrons into the benzene ring, but the electron withdrawing groups withdraw electron from the benzene ring. And then there are some that because they have multiple substituents of electron withdrawing group, which greatly increase the acidity of phenol. That if you have multiple substituents of electron withdrawing group on the benzene ring, when there's an electron withdrawing group, it will be pulling out an electron from the benzene ring, and so making the benzene ring to be more positive. Because when you push electron in, like the electron releasing group, when they push it in, what we have is that there is more electron available in the benzene ring, and the benzene ring becomes more electronegative and becomes more richer in electron, and so the negative charge is more stabilized. But when you pull out electron, when you have electron withdrawing group or substituent on it, it tends to pull it away. And then we now call the both of them the electron releasing group. We say that it is an activator. So methyl groups or all alkyl groups or ethers, they activate the benzene ring because they push in electron to the benzene ring. Whereas electron withdrawing group like NO2ClOH, they withdraw from the benzene ring, so they deactivate it. So now this is a benzene ring. Now, if you have a methyl group inside the methyl group, we push electron into the we push electron into the benzene ring, and so it makes the benzene ring even more stabilized. The same thing with this. But if you have electron withdrawing group, they withdraw electron towards each other. They withdraw the electron towards each other, and by doing that, they deactivate this phenol ring, and so that's also determining so like I wrote here, I said electron withdrawing substituents make a phenol ring more acidic by stabilizing the phenoxide ion. So when we have electron withdrawing group, it deactivates the benzene ring. But when we now form the phenoxide ion will now be more stabilized, because the phenoxide ion is a base, so it is more stabilized, and through the localization of the electric negative charge through inductive. If you recall that I said that what we now have, let me show you. Let me recall. What we now have is this phenoxide ion that is now a negative charge. So because they can move around, then it is more stabilized. That's what happens. So this is just the ionization of the pKa of different types of substituents of phenol. The pKa tells you about their acidity. The smaller the Ka, the more acidic they are. So that means phenol is the most acidic and all that like that. So you can check that later. Phenols are first isolated from coal tar, and they are important industrial chemical processes. And as I've told you already that they are majorly used for plastic adhesive astringents, and so many, even in pharmaceutical processes, they are used there. And this is the preparation. Industrial preparation is from benzene sulfonic acid in the presence of sodium hydroxide at a very high temperature, and you get your phenol. And you can also prepare them from chlorobenzene in the presence of sodium hydroxide, water, and also at high temperature, you also get benzene. So these are very old methods for preparation of phenol, and you can get them online in those things I posted. You can check them later. The reaction actually occurs in the first one, the reaction occurs addition elimination reaction, and the second one is elimination addition reaction. So going on with this industrial process, you have to use readily available material, which is cumin is a very available material, and cumin is actually a natural product that is found in essential oils. Essential oils are found in aromatic plants, plants that smell. You know, there are some plants that have aroma. When you touch them or you pass by them, you perceive some smell. So compounds are plants that have essential oils, they have cumin. So cumin can be isolated from them. So reaction of cumin, oxidation of cumin in it, we give cumin hydroperoxide, and then acidification of it, we give phenol and the acetone. So that is an industrial process that is also being used, unlike that old method that I mentioned. So we can get them from cumin for industrial processes only, not lab work. But for labs, when you want to prepare phenol, the best way to go through is via the iridiazonium salts, because the iridiazonium salts will give a particular substituent or intermediate that is a very good leaving group, and we bring in the OH fast. And this is done by reaction of the aryl amines with nitrous acid, which is HNO2. So this is a nitroaniline. This is aniline. So NO2 on this makes it nitroaniline. So when you react, when you react sodium and nitrite and sulfuric acid, that will give you the aryl amines. So this is aryl amine with nitro, that will give you the nitrous acid. So the nitrous acid is generated in situ. That's what I want to just mention. The nitrous acid is generated in situ using sodium nitrite and sulfuric acid. You get your nitrous acid being generated in situ. It is not a reagent you can find on the bench. So you generate it in the reaction vessel there. You react it. When you react sodium nitrate and sulfuric acid, you get your nitrous acid. And when you now react it with an aryl amine, then you get your aniline. You then get your nitrophenol. So this is what we call an aryl amine, because this is an amine. This is an amine. So when you react it with nitrous acid, which is generated in situ, then you get the nitrophenol. So the nitrophenol that we get now, let's go on. So this is a substitute. This is a substituted phenol that you have gotten here. So let's see some other preparation that will give you just phenol only. So number one here is reaction with sulfonic acid. Then we can also have reaction reaction of chlorobenzene with base can also give you phenol. Reaction of oxidation of cumene can also give you, this is cumene, oxidation of cumene can also give you OH, like I've mentioned, even for industrial processes the other time. And the hydroxylation of the diazonium salt. So this is diazonium salt that you get. This diazonium salt is a very good leaving group. This N2 plus. In fact, you can use it to prepare so many substituents of phenol because it can easily leave and any substituent can come in. But this time around, it is OH that we need. So it can be used. It's a very useful reagent. So it occurs in the presence of sulfuric acid at 100 degrees. So like I said, that the phenols are weak acid because they can release proton and then form the phenoxide ion. So the azoxide group can donate their proton for their acidity, and this also defines their reactivity with bases. Because of that, they can react with bases like sodium hydroxide to form salts, and they can also undergo electrophilic substitution reaction. So benzene ring in phenols undergo this reaction just like normal benzene. Non-normal benzene generally undergoes aromatic electrophilic substitution, what that means is that an electrophile will react with the benzene ring because the benzene ring is a nucleophile. It has excess electron. Any species that we call a nucleophile, like we have been taught before, are species that have negative charge, have excess electron, they are electron rich. And any species that is electrophile, they are electron poor, they are electron deficient. They call them positive, they are positive. So because benzene has 6 pi electrons moving around inside it because of the 3 double bonds. Anytime you see a double bond, what it represents is a pair of double bond, that is 2 pi bonds. 2 pi bonds. So 2 times 3, that is 6. So it's at 6 moving around. And so it is a nucleophile because it is electron rich. So that is why a nucleophile cannot attack it. The only substituent that can react with it will be an electrophile. So they undergo electrophilic substitution reaction, just like benzene ring. For example, nitration, sulfation, chloration, and all that. They can also undergo oxidation. When they undergo oxidation, so in water, phenol is a weak acid. It reacts with water. I think I've given you reaction with water before. It reacts with water. Water now acts as a weak base because it's stronger. And with sodium hydroxide, it reacts with sodium hydroxide to form sodium phenoxide. I've also given you this before. It can also react with sodium. All these I have here are properties of acidic compound. Any acidic compound will undergo this. They react with base and they can also react with sodium, just like any other acidic compound. Please, if you have question at any point in time, just use the reaction button to raise up your hand so I can allow you to ask your question. Thank you very much. So these are just the reactions again. This is sodium reacting, so it's called sodium phenoxide, and then this is another one. So, and this is the reactivity order. That is, methane is less than, so HF is higher That's the reactivity order that when they want to react. So phenol, this is where phenol stands in acidity order. So that means all the ones on the left are less acidic than it, and all the ones on the right are all more acidic than phenol. It can form ester just like alcohols because it has OH. So the OH of the phenol can actually, this OH can react with an acid to form an ester, just like the normal esterification reaction. So it can undergo esterification reaction. We all know that esterification reaction occurs in the presence of acid. The catalyst used is always acid. Then this is salicylic acid. This salicylic acid can react. So this is a phenol. This is a substituted phenol. The first one is also a substituted phenol. The second one is also a substituted phenol. But yeah, we are not calling it a phenol. Notice that become an acid, but at least there is OH there because it is now an acid. Because I told you that if there is COH, then that takes preference. So that's why it is called salicylic acid. But because of the OH here, it can react with, when you want to undergo a esterification reaction, it's not only acid you can use. Apart from carboxylic acid, you can use some of the carboxylic acid derivatives that we know. You can use ester, you can use acid anhydride, you can use acid halide. The only acid derivative you cannot use is the amide, because the amide is weak. But the other three, you can use acid, you can use acid anhydride, you can use acid chloride. Those three, you can use it to react with alcohol, and you still get your ester. So this is how aspirin, the common aspirin that we use at home, although I don't think we use it much in Nigeria. They use it for pain, and the low dose aspirin, they use it as an anticoagulant. People that have hypertension or cardiac issues, they use low dose aspirins, between 17 and 80 milligrams per day, so that their blood can thin out, because we have to be relating all these chemicals to everyday lifestyle. So that you know that most of these compounds that we talk about, they're actually important to us. So they use it every day so that there will be no clogging. Because if there is a clot along the arteries, there may be problem. There might be heart attack. There may be blockage of the blood will not get to the brain, and that can lead to also paralysis and all that. So elderly people, especially those that have high blood pressure or cardiac issues, they are advised to use low dose aspirin every day. But the high dose aspirin, like 150 milligrams, is used to counter pain. It is a pain reducer. And so this is how it is prepared. It's just an esterification reaction for you to know. So you can look at this problem, and then the solution is just an esterification reaction using an anhydride for the compound. Then we have ether formation. Ether is different from ester. The functional group is different. Ether is actually when there is oxygen in between two alkyl group or two aryl group, like we have here. This is an ester, an ether. You can see that there's oxygen in between. So that is an ether. So phenol can be used to form an ether. So in the presence of an alkyl halide and an alkali, this is the ether. So the oxygen is in between the benzene ring, an aryl group, and the alkyl group, which is the ethyl group. So because they are more acidic than water, it is possible to generate a phenoxide in situ using sodium hydroxide. Then once the phenoxide ion is generated, that's the first step of the reaction. Once the phenoxide ion is generated, then the alkyl bromide reacts with the phenoxide ion to form the ether. It's a straightforward reaction. The reactions of phenols, the C ring, the carbon ring. A carboxyl group is very powerful activating substituent. I've mentioned about activators and deactivators when they are on the benzene ring. I think I mentioned it a while ago. And so OH, the hydroxyl group, is one of the powerful substituents that can be on benzene that will make it an activator. And when that happens, that means it can direct another substituent that is coming on the benzene ring. It can direct it either to the ortho or to the para. Maybe it is a deactivator that is coming. A deactivator will, if it is not OH that is here, if it is a deactivator like NO2 that is here, it will direct to the meta position only. But the activators direct to the auto or to the para. And if they are very strong, they will direct to both auto and para at the same time. So because OH is a very, very powerful activating, it will direct, the reaction is fast, and you can see that it can direct to the auto position. So it has directed to the auto position because there is something already on the para position. That's why it's directed to the. But supposing it is just OH that is here, then this NO2 will go both to the para and the auto position. But because there is CH3 here, that's why we have it here. So this is cresol. I'm giving this one before. This is cresol. You can say p-methylphenol. Either you call it p-methylphenol or you call it, this is the trivial or common name, which is paracresol. And so this is what we have. So when an incoming substituent comes on benzene ring, they don't just go to anywhere they like along the carbon chain. They are directed to a particular position depending on what is on the benzene ring before. Whether the substituent on the benzene ring is like OH, that is an activator, or NO2 or any other deactivator, then that will push it to the meta position. So nitration of benzene occurs just like we have for so nitration of phenol occurs just like we have for benzene. You know that nitration of phenol, the reaction takes place in the presence, apart from NHO3, the reaction occurs with dilute nitric acid at room temperature to give mixture of 2-nitrophenol and 4-nitrophenol. Like I said, it can direct to the auto position. It can direct to the auto position. It can also direct to the para position. So that's why it is giving two products. So it will give the 2-nitro position, or what you can also call the O-nitrophenol. You can also call this one the p-nitro position, because I've told you that OH is a very, very strong activator. So with concentrated acid, this is what happened. Note that the first reaction is with dilute nitric acid. If we make the reaction more vigorous by using a concentrated acid, it will go to all the positions of the auto and para immediately. So you now have 2, 4, 6. You can see that this position 2 and position 6, they are both auto position, and position 4 is the para position. All of them are attacked. All the carbon are attacked immediately because you are using a concentrated acid. So depending on the product you desire, that should be able to determine what you are going to use. Then this is sulfonation. Sulfonation also occurs just like benzene, and this is achieved by the reaction of sulfuric acid. At low or high temperature, you still get it. But to get at low temperature is different from what the product or the substituent attack is different. At low temperature, the sulfonic acid goes to the auto position. At very high temperature, it goes to the para position. So you can see that reaction in organic chemistry or chemistry generally is defined by so many parameters. A change of temperature is important. The temperature you are using is important. The concentration or dilution of the reagents you are using is also important because it can change the mode of the reaction. Whether you are using dilute, you are using a mild, or you are using a concentrated. The same thing when you were taught reduction and oxidation reaction. You are taught that we have strong oxidizing agents, mild oxidizing agents, and weak oxidizing agents. So depending on what you use, that is what will drive your reaction to the forward reaction and will determine your final product. The same thing we have here. So you have to choose our reagents wisely. Very, very wisely. So this one, we have 2-methyl group already attached to the phenol, 2,6-dimethylphenol. In the presence of sulfuric acid at high temperature, it pushes the sulfonic acid to the para position. OH can only push incoming. Please note that OH on the phenol can only push incoming substituent that attacks it to either the auto position and the para, never the meta position. So that is very, very important for you to know. And this is halogenation reaction. It can be done using 1,2-dichloroethane. And you can see that it pushes to this pushes only to the para position. and the yield is very high, 93%, which is very good. This is also halogenation, but there's water also added, bromine water. If bromine water is added to a solution, that means bromine in the presence of water. The reaction occurs in the presence of water. So the bromine water is decolorized and a white precipitate is formed. This is one of the tests for phenols. We are going to do that in the lab also when you come to for your practicals. Test for phenols using bromine water, because there is a color change that will occur that we see, and we know that a precipitate has been formed, and that precipitate is actually a white precipitate which smells like an antiseptic lotion. I believe all of us know how antiseptic lotion smell, like a Dettol, something like that. So that's it. So most of these processes are what they use to do, what they use in industries to produce so many things that are useful to us. Then the Friedel-Crafts reactions. We have two types of Friedel-Crafts reactions. We have the Friedel-Crafts alkylation, and we also have the Friedel-Crafts acylation. Both of them make use of a catalyst, which is called Lewis acid. So when alkyl halide reacts with phenol, in the presence of this Lewis acid, there's alkylation reaction occur, because the alkyl group of the alkyl halide is taken and added to the benzene. You can see it here. So now we now have alkylation occurring. And if you look at this also, you see that it can only occur either at auto position and also at a para position. But if you do if you use alkanoid chloride, or what we commonly call acyl chloride or acetic chloride, what you are going to have here is COR. So that is a ketone. You have COR. Your R can be CH3, acetyl. So it will be acetyl. COCH3 is called the acetyl or the AC group. So that's why I said that we have it as Friedel-Crafts alkylation like this one. And then this COR represents the Friedel-Crafts acylation. But both of them use the same Lewis acid as their catalyst. So these are examples here now. This is cresol. In the presence of this alcohol, this is a tertiary butyl alcohol. You can see that the carbon is not carrying any hydrogen. We have done that in the last class, the classifications of alcohol. So this is the reaction. What we now get is an alkylation. So this alkyl has been, this compound has been alkylated. So the phenol has been alkylated. This has been transformed here. So we have it here now. So it's alkylation. So this is Friedel-Crafts alkylation. But if you now use this is acetic chloride I'm talking about. If you use this acetic chloride, you can see that the acetic chloride is just the same thing. What has just been removed is just the Cl. So this acetic chloride, this acetic group, the acetic group attaches here. And what we now form here is now a ketone. This is a ketone has been formed. So you can either have it, so you have both of them, either at auto position, at para. Like I always mention, phenol will only move substituent to the para or to the auto position. So phenol esters are often prepared in 2 steps. So this is just a preparation of a phenolic esters are often prepared in 2 steps by means of price rearrangement instead of direct acylation. You can have it, number one, the step as formation of phenyl ethers, and then the migration of the AC group, which I mentioned. This is the AC group I've been mentioning. You can call it the AC group or the acetic group. There's a migration of it from phenolic oxygen to the ortho and the para. So it moves. So when this occurs, there can be migration. So after reaction, and you get this, there can, so this is a little bit deviation from what we have in the last this thing. Here you see that the AC group attacks and the ortho and the para. But in this one, it is called the Fries rearrangement. There is rearrangement such that the reaction, this is an intermediate. The reaction occurs by this attacking first, reacting first, forming an ester first. Then when it forms the ester with the OH, then there's now rearrangement to what the ketone that we actually determined. And so that's what happens here. So that's a little bit deviation from the normal acyl Fourier-Clapeyron acid reaction. Then it can also react with diazonium salts. You remember I mentioned that these diazonium reactions are very, very important, and they are very good living groups. They can be used to prepare, in fact, we use it to prepare phenol itself when we react it with water, and then it forms phenol, so which is here. So this is benzene diazonium chloride. So it will form phenol in OH, and then so this is 3-hydroxy 3-methylphenyl oxybenzene, which is a red precipitate. So they react with diazonium salts to give azo compounds. Those azo compounds are like dyes. They are dyes actually. They can use them as dyes because they have distinct colors. This one is a bright red precipitate, and this is usually used in the identification of aniline. So in the lab, when you want to do test for amines, this is one of the tests that we are going to do for test for amines to show that amine is present. You can also react with arene diazonium salts. So this is arene diazonium salt, and this is what we get. This is still from the other one. This is still from here. It's the same thing. It is this is the reaction. This is another reaction of the azo dye that is formed from naphthenol. So it reacts with this. This is an amine group reacting with it. Okay, I mentioned salicylic acid the other time. We have done this before. This is just the spread out of the reaction, whereby the phenol is used to prepare the salicylic acid. So the reaction is actually called the Kolbe-Schmidt reaction. And the acidity converts the sodium salt to salicylic acid. So this is just the procedure, starting from the phenol reacts with, is converted to sodium phenoxide, and the sodium phenoxide, in the presence of carbon dioxide, forms sodium carboxylate, and then we have the salicylic acid. So this is salicylic acid. Then their reaction with phenols to form phenols. This is an oxidation, oxidation of phenols to form quinolines. So this is an oxidation reaction whereby when the oxidation occurs, we form quinones. And for quinones to be formed, the phenol must have 2OH. So this is, okay, this is hydroquinone, this is quinone. Hydroquinone, quinone. They call it hydroquinone, I think. Okay, they call it hydroquinone because hydrogen has been added to the quinone. This is quinone and this is hydroquinone. Phenols are easily oxidized to quinones using a catalyst. So this is the catalyst that is used. Iron trichloride is used to form that. And you can see that the reaction is actually reversible. So the hydroquinone can be converted to the quinone, and the quinone can be converted to the hydroquinone. And then it can also be done, the phenol can be converted to hydroquinone directly without going through this process. It can be converted directly to this quinone, this benzoquinone, which is also the quinone. It can be converted by using this Fremis salt, this reagent here. Then we have the benzoquinone directly from phenol. Oxidation of phenols. Okay, that's what I just mentioned just now. This is the one we did just now, whereby you get the benzoquinone in high yield, and then this is the other one that we have, whereby we have the hydroquinone being. It's just the two that we have here. So this is the benzoquinone, which is the general name is a quinone, but this is actually benzoquinone. So just here we have it upside down here. It's just the same thing. So benzoquinone to hydroquinone, the hydroquinone to benzoquinone. It's just the loss of proton here, and then you have the oxidation. So the reverse reaction here is the oxidation, whereas in the other one, the forward reaction is the oxidation. And here, this is the oxidation of phenol to give the benzo phenol in very good yield. Phenols are very, very important in nature. They mediate electron transfer processes in energy production through their redox reaction. So they can undergo redox reaction. A species that can undergo redox reaction is a species that can undergo both reduction reaction and oxidation reaction. That is that species in it that can undergo that. And this is in living organisms. I will skip this, but just know that they are very, very useful in nature. Then we have a reduction. Phenols are reduced to corresponding aromatic hydrocarbons by distillation with zinc. When you distill phenol in the presence of zinc, distillation always occurs. Anytime you hear distillation, what that tells you that high temperature is affected. So it changes. And this is actually what we call aromatization. It aromatizes. So many compounds, so many substituents of phenol generally, when you react them in high temperature with certain metals like zinc, tin, sometimes even maybe copper or whatever, they aromatize. And then what you get is just the benzene ring. So it happens that they just aromatize and all the substituents disappears. So they are reduced. That's, I mean, maybe the right word I should say that they are just reduced to the benzene. So they are reduced to the corresponding benzene, which is the, so at high temperature, zinc, even tin, SN, also you can use tin and so many other metals. At high temperature, they turn any substituted benzene, they reduce them to their aromatic. So it's not only zinc we can use, that's what I'm just saying. You can also use tin and so many other ones like that. Nitrosation is a reaction with a sodium nitrite for you to get a nitroso compound. This one is very straightforward, but the reaction occurs at a very low temperature of 0 degrees and in the presence of sulfuric acid, which activates the reaction to get the nitroso. Any compound we talk about is preparation. Know that that compound is useful to humanity one way or the other, either as a solvent, as a compound that can be used to prepare as a raw material to prepare other compounds. They are also useful as products that we use at home, in household products, industrial products. They're also useful. Some of them are also, even many of them are also used medicinally as pharmaceutical products and processes like that. So many of them are very, and this naphthol, most of them are very, very good uses. Then you can also form resins. Resins are plastics. So they are the basis of plastics. So phenol can react with methanol in the presence of any alkaline condition to give addition products, which are the basis of the plastics. And that is the formation of resin. Resin is very, very important when you talk about products. So when we ask you about the important uses of phenol, these are some of the things I expect you to mention. All the uses that have been mentioned, that has been talking about, these are some of them that you have to actually mention. Then other uses, just like I was saying, the uses of phenol as disinfectant due to their antimicrobial properties. Phenols are used in antiseptic products. They are used as industrial chemicals for the production of plastics, resins. They are also precursor. When I mention as raw materials to other compounds, that is the same thing as saying that they can be used as precursors to prepare other compounds that are important or other solvents like acetone, like chloroform and others. Because phenol itself is a solvent, so it can also be used to prepare other solvents or other chemically important compounds. It can also be used medicinally. I think I've mentioned all this in the former slide. Phenolic compounds, they can be used as antibacterial, once they have antiseptic properties, they can be used to mop up microbes at any time. So that means phenol can be used to wipe, just like ethanol too. You can use them as antimicrobial. You can use them to wipe tables, clean surfaces. You recall that even the common this thing that we use, what do we call? How can I forget? Sanitizer. The common sanitizer that we use is ethanol that is inside. Ethanol has some additives because they have antiseptic properties. The same thing with phenol. But just that some are safe to use, some are not safe to use. Ethanol is safe to use at very low dilute concentration, but we don't use phenol like that because it has other toxic effects. But that doesn't stop it from having antibacterial and antiseptic properties. Then they can also be used as antioxidants, especially when we talk about phenol, not phenol as in phenol, phenolic compounds. That means we are talking about substituted phenols. Some substituted phenols are safe to use. And those are the ones I'm talking about, not phenol as it is phenol. So some phenols, that is some substituted phenols or derivatives of phenols that are actually plant-based. Examples are the carotenoids, flavonoids. They have plenty antioxidant properties. Even tannins. Tannins have a lot of phenols in them. I believe all of us have heard of tannins before. They're also very useful products here and there. Flavonoids, we have a lot of pharmaceutical products that are derived from plant-based compounds called flavonoids. They have a lot of OH on them. So they contribute to human health and help us to stay healthy. So I think that is the end of my lecture on phenol. Please raise up your hand if you have a question so I can explain. If there is any part of the notes of the lecture that you do not understand, you can please let me know. So are we saying there is no question? Because I want to stop the class now. I have a meeting I have to prepare for. We have faculty board meeting and I have to go there. Okay. Akin Dikpe is raising up. If you don't raise up your hand, don't talk, please. The only people that raise up their hand that I want to go. Akin Dikpe is the one raising up the hand. If you want to ask a question, raise up your hand. Akin Dikpe, you can unmute and ask a question, please. Akin Dikpe Oyebisi.
Okay, ma'am. My question is that why is it that phenol does not push substituent group to metal, but only push to ortho and para?
That is a very good question, Meta. Although I've explained it, maybe you are not paying attention. I explained it broadly that phenol OH is an activator. It pushes electron into the benzene ring. So any species on benzene ring that pushes electron into the benzene ring will activate the benzene ring. What do you mean by activating? The benzene ring already has 6 pi electrons. I believe you know that because of the double bonds. So it is rich in electron. So anything that will make the benzene ring to be activated must be a species that will also push electron to the benzene ring. Because if a species on the benzene ring tries to withdraw electron from the benzene ring, it is going to destabilize the benzene ring. Because benzene can only undergo electrophilic aromatic substitution. Only electrophile, a positive species, can attack the benzene ring. So that means the benzene ring must remain electron rich. So all those species like OH, like alkyl group, like esers that have electron to donate to the benzene ring, when they are on the benzene, they activate the benzene ring. And they are known, it is a fact that they push electron to the I think you are going to be taught when you are there's somebody that will teach you benzene. I think you have been taught benzene. If you are in the class where they teach you benzene, they will have taught you all these things, or maybe they're still going to teach you, but I think they have taught you benzene ring. I want to check. They will have taught you now why about these deactivators and activators, and why substituted benzene, if there is a mono substituent on the benzene, why they will push to the ortho and to the para. So it is only when we have activators that help the benzene ring to be able to stay as a nucleophile and electron rich, that will now allow an electrophilic compound to come in. Those are the species that we push to the auto and para. But if it is a species that is a deactivator, that is a species that withdraws electron from the benzene ring, like NO2 or those carbonyl compounds. Do you understand? They remove electron. They try to withdraw electron from the benzene. And when they withdraw electron from the benzene, they will make the benzene to be electron deficient. And that means the benzene will tend to be delta positive. So how can an aromatic electrophilic substitution occur? Electrophile is coming. The electrophile is always carry positive charge. And so if the substituent on the benzene is also pushing, removing electron from the benzene and causing it to be a bit electron deficient and positive, positive cannot attack positive. So that's why they call them a deactivator. In that way, they are deactivating the benzene, and they will not allow an electrophile to be attached to react with the benzene. But so OH and other activators are good for the benzene. When they are on the benzene, they move to the para and to the auto. But for the activators, the NO2s and so on, they move incoming electron to the metal. The mechanism of those reactions, I did not bother because I know you have been taught the step, because you have to have, there are some canonical structures or resonance structures that they will have given you how this occur. Maybe about, just like I gave you for the phenoxide ion. I gave you some resonance structures. They will have given you how electrons move around and how these things move to the auto and para or metal. They are not magic. They are things that can be explained, and they have reaction mechanisms. And I know that they have taught you. Maybe you did not attend that class, but you can read it. Notice everywhere. You can go online and go and read it again, because somebody has taught you already. Any other person? Have I answered your question? Is there
Yes,
another person
ma'am.
raising? Thank you very much. Can I have any other question? If you want to ask a question, please raise up your hand like she did, so I can call you. Okay, Ayodele Oreoluwa, please unmute to ask your question.
Yes, ma. Good morning, ma. Ma, it's not a question. I wanted to ask if we could get your recording.
You are not going to get my recording, but you get the notes, because there's no need to record. It is already on YouTube. I placed the YouTube on your platform. So if you go to that YouTube, you can just watch it on YouTube, the notes. So there's no need to give you recording. Do you understand what I'm saying?
Yes, ma'am.
I put the YouTube link on your platform. So just go and click it. Then you can listen to it all over again. The same thing with all other classes. Thank you very much. So if there's no other question, I think we can all go. Thank you. I will get your attendance from my own recording. I'm recording, so I will get your attendance here. Thank you for coming to class. So bye for now, everybody.
Thank you, ma'am.
Thank you,
You're
ma'am.
welcome. Thank you. You're welcome.
Thank you.
Thank you.
You're welcome. You're welcome.